All right, so let's look at an example of using the Arrhenius equation. So Arrhenius equation, of course, has to do with activation energy and the pre-exponential factor and those kinds of things. So we're given a reaction. We're told this reaction has a rate law of the form rate equals to K. This with the half-life of 100 seconds at 25 degrees Celsius. And we're asked some questions. We are asked to determine the activation energy given that K has a value of this at 55 degrees Celsius. So the question is, how do we calculate activation energy? Well, we can use the fact that ln of the proportion of two K values needs to, or that's the thing that we need to get, is going to give us some relationship to the activation energy. And then we can use those two at the different temperatures to calculate the activation energy. So the rate constants at two different temperatures can help us calculate the activation energy. And the question is, do we have two rate constants at two different temperatures? Well, we're definitely given one at 55 degrees Celsius, and we're given some information about the reaction at 25 degrees Celsius. And now, of course, the important point is we can identify this is a first order reaction, right? So this means the half-life follows the expression T a half is equal to ln of 2 divided by K. So that means K, well, let's make it a subscript at 25 degrees Celsius, is going to be equal to ln of 2, and the half-life at 25 degrees Celsius is 100 seconds. So you should get a value then of 6.93 times 10 to the power minus 3 per second. And that is, of course, at 25 degrees Celsius. So let's maybe make a summary of what we then know. So we have K, 25 degrees Celsius is also known as 298 Kelvin. So let's call it K298 is equal to then 6.93 times 10 to the negative 3 per second. And we also have K at 55 degrees Celsius, which is 328 Kelvin. And this one is given as 1.69 times 10 to the minus 1 per second. Of course, we're also given the two temperatures. So this goes along with T, let's call this one T1. So it's 298.15 Kelvin. This one T2 equal to 328.15 Kelvin. So whatever subscript you want to use, you can also just call this one K1 then. You call this K2 then. It's irrelevant which one is 1 and 2. The ratios will sort themselves out. And of course, R you use as 8.3145 joule per Kelvin per, in this case, mole reaction. Right. So that is all our values. You'll see why I give you the values now, or write the values, because it's just a mess to plug everything in. So we want to solve that equation on top there for EA. So let's start by writing it in a better form. So ln of K2 over K1 is equal to EA 1 over R. And then how do we get the sum of two fractions? Well, we say 1 over T1 multiplied by T2 over T2 minus 1 over T2 multiplied by T1 over T1. Right, so we started with 1 over T1 minus 1 over T2, and then to get a common denominator, you multiply by a pseudo 1 in each case. So this, you multiply by 1. All right, in each case, but what contains the other one? So the other fraction. So let's leave the left-hand side for as is for now. So we get EA 1 over R. So we get T2 minus T1 over T1, T2 or whatever. So T2 minus, oops, maybe make me not skip steps. Over T1, T2 minus T1 over T1, T2. Okay, gives us EA 1 over R, and then we can put those together. So it gives us T2 minus T1 divided by the same thing. All right, we want to solve for EA. We can plug the R in there, so we eventually get EA multiplied by the big bracket T2 minus T1 divided by R T1 T2. Solving for EA, you'll get on top, you'll be left with R T1 T2. The bottom will be T2 minus T1, and this will be multiplied by ln, so just have to put that in bracket, ln K2 over K1. And then plug in those values that you have there, and we're going to leave it in kilojoules. So you should get 86.6 kilojoule per mole. If you just use 8.1345 mole, but it's mole reaction, because activation energy is per reaction, so mole reaction. All right, so that's the activation energy for the reaction. So remember, if you're asked to calculate activation energy, you're looking for two rate constants at two different temperatures. So that's essentially all that you're looking for. And in principle, you will have to be able to do this kind of manipulation on your own. So yeah. B question asks, determine the value of the pre-exponential factor A. Well, the pre-exponential factor A refers to the base equation of K. Oops. Why does it keep on jumping? K equals A e to the power minus EA divided by RT. Right? So that means we can solve this for A. So in general, A will be equal to K e to the power EA over RT. I mean, so you just basically drop the minus. And we just need to use either one of our sets of data. So if we use K1, we use T1. If we use K2, we use T2. So you can use both and check if you get the same answer. And so in this case, I'm going to use the set of data of 1. So K1 e to the power EA over R T1. We plug those values in. K1 is 6.93 times 10 to the power minus 3 per second. E to the power, of course, your EA, you don't round, you don't use your round value, so the 86.6 whatever kilojoule per mole reaction. Which is divided by 8.3145 joule per Kelvin per mole reaction multiplied by, so we use the K at 25 degrees Celsius, so our temperature is 298.15 Kelvin, which will give you a value of 1.03 times 10 to the 13 per second. And it's interesting. I mean, you see that's massive value, right? Because A implies it is collisions per second. So, I mean, that's what the per second. So it's so many collisions per second. That's a very many collisions that happen per second. It makes sense. I mean, because there has to be a high percent or high number of collisions, because this doesn't say all of them are successful. It just says there are so many of them. And then depending on the temperature, a higher percentage of them are successful. Right. So, well, actually, depending on the temperature, I mean, it's one of those more difficult concepts because of their orientation and whatnot. But if we have more collisions, more of them will be successful. That kind of thing. So it's giving it's a very, very large number, and A is normally a very large number because molecules constantly collide. There's a lot of molecules. I mean, in 1 mole, there is an unthinkable amount of molecules. I mean, there's 10 to the power 23. That's a massive order of magnitude amount of molecules to have in 1 mole of a substance, which is just like sometimes not even a handful of something. And I mean, to imagine if you have some gas or whatever, if you have 1 mole of that gas, I mean, just imagine how many collisions there is potentially per second in that 1 mole of gas. And so in other words, it makes a lot of sense that should be a very high number or very high frequency for the reaction. And it links to the reaction rate, of course, and how quickly the reaction proceeds. All right. But anyway, so that's the Arrhenius equation. You know what activation energy is. It's the amount of rounds of energy required per 1 mole of the reaction to proceed. And A is then, of course, the number of collisions that happens per second that reaction or that takes place per second in the reaction. Right. Okay. Thank you for watching.